So in this part 4, we are going to discuss the effects of defect structures. So we have two effects of defect structures. First one as solid electrolytes, okay, where the passageways created can be zigzag or straight channels, which are used as routes for ions to move, allowing the solid to behave as an electrolyte. So the solid electrolytes generally display Frankel defects and can be expected for large, highly polarizable anions and highly polarizable cations of low charge. So, and for the second one as semiconductors, okay, so we have two types of semiconductors. The first one is the N-type and the second one is the P-type. So let's go to the first one, the N-type semiconductors. Okay, so this is where we have a silica or silicon. Okay, this is silicon doped with a phosphorus. Okay, this is one of the impurities. Okay, impurity, we add on the impurity of phosphorus, and what happened here? Okay, there will be extra electron. Okay, an extra electron of every phosphorus atom. Okay, so this extra electron will be removed, okay, can be removed, okay, by applying a voltage across the solid. So when we have free moving ion, what happened here? Okay, these the semiconductors here can conduct electricity. It can conduct electricity based on the extra electrons. So the major carrier of the N-type semiconductors is extra electrons, while for the minor charge carrier for these N-type semiconductors is the hole or the vacancies. Alright, so the free electrons can then move through the structure and function as conduction electrons. Okay, so these usually phosphorus can be considered as pentavalent impurities. Okay, alright, and then the impurities of this type are known as donor impurities because we have extra of electrons. Okay, and they provide the conduction electrons. Okay, this is the spare or the extra electrons. And solids containing the donor impurities, usually we call it as N-type semiconductors, where the N actually stand for negative, okay, from the charge of the extra electron. Okay, so that's all for the N-type semiconductors. And for the P-type conductors, P stands for positive. It means this conductor has electron deficient, is an electron deficient. Okay, so here we have a silicon doped with or integrate with boron, which is a trivalent impurity. Okay, so when we add on the boron or integrate the boron, there exists a single vacancy, okay, in the bonding orbital for every boron atom. Okay, so here when we have the vacancy, it is possible to excite a valence electron from a nearby silicon into this vacant orbital. Okay, so here, okay, the vacancy created at that silicon can then be filled by an electron forming a neighboring silicon atom, and so on. So the major carrier for the P-type semiconductors is the hole or the vacancy here. Alright, and then the minor carrier for these P-type semiconductors will be the electron. Okay, right, so in this manner, electrons move through the crystal in one direction, okay, while the vacancies or positive holes here move in the opposite direction, and the solid becomes an electrical conductor. Okay, so the impurities are from the trivalent impurities that are electron deficient, and we can call it as acceptor impurities. Okay, so the semiconductors that contain these acceptor impurities, we call it as the P-type semiconductors. Okay, so that's all for this part 4. Okay, so guys, please I hope you guys enjoy this video, and don't forget to like and also comment and subscribe to my YouTube channel. So I'll see you guys in the new topic. Okay, so that's all for this part, and thank you everyone. Bye.